Today we will do some further studies of this crop picture from 2018 in Czech Republic and try to understand what it means. What you can see here, we've got a wire coil of some kind, or two wire coils, and a spinning disc with current running through it as it spins, and three things on the outside. So what I've done, I've taken three big wire coils, about 100 millimeter each. They look like that. And we're going to put an aluminium disc over it like that, so it can spin. You can see there's quite a good relationship between that, and we're going to use a three-phase power supply, turn on the power, and see what happens. You would expect a horizontal induction to make the thing spin. If we use three-phase power, so it should spin a bit. It won't be a surprise, but let's do it anyway and just see how it works. Okay, now we've put 150 millimeter aluminium plate, 3 millimeters thick, on top of these three wire coils. It looks a bit like the crop picture, not perfect. And it's wired up to three-phase power from this variable frequency device. So we're going to turn on the power three-phase and see what happens in terms of hertz. There's 11 hertz. And remember, 50 hertz is 220 volts, so this is about 5 times less. 16 hertz, it's starting to wiggle. 20 hertz, now it's starting to turn. 25 hertz, it's turning. This is just a horizontal induction motor. 30 hertz, it's turning quite nicely. 35 hertz, even more. Now we've placed an even bigger aluminium plate over those three wire coils, and we're going to turn on the power again. 10 hertz, 20 hertz, not spinning yet. 25 hertz, it begins to spin like a horizontal induction motor. And 30 hertz, that's as high as I want to go without stressing all of the current. That's about 120 volts. Next we're going to try the small disc at 50 hertz, which is 220 volts when it reaches power. Just quickly, because the coils get hot. Let's watch it start. We'll also try the large disc briefly at 50 hertz or 220 volts, just briefly. The reason I don't run it longer is not because of the power supply here, because these wire coils overheat. But it's not too bad, is it? Now most induction motors use iron somewhere on the rotor, aluminum or copper, and have a piece of iron. It turns out the rotating magnetic field is strongest right near the center of these three coils. So if we take another iron bearing and we just sticky tape it on to the center of the axle, we put some power on, the torque from that iron will make it spin more easily than before. Here we're at 25 hertz, 30 hertz. It's spinning quite nicely. It probably improves the hertz speed by about 5 hertz. That's with a little bit of iron added in the center. Even without the aluminium being there, you can see the iron definitely wants to spin as we put up the rotating magnetic field to, say, 35 hertz. Sheet of aluminium likewise spins more easily with a little iron bearing placed in the center. And that's just 25 hertz. It's spinning quite nicely. Beautiful, isn't it? Put the 30 hertz. Very satisfactory for an induction motor. 35 hertz. Quite all right. So in summary, what we have found here is if we take 3 wire coils and wire them as UVW with 3-phase power and put any sort of aluminium plate on top, for example that one, and then we turn on the power, the rotating magnetic field, which goes that way or that way, will make the plate spin by Lenz's law induction, just like for a vertical induction motor like we use everywhere else in cars and lawnmowers everywhere. Now this may or may not represent what's seen here in the crop picture. We see 3 coils and something spinning with a wire coil below, but this is supposed to give UFO lift, and I don't think it's going to be enough. There must be something else I'm missing, because really what we're looking for UFO lift is warping of space by an electromagnetic field. So at the very most we can just consider this a first step toward further progress, and we'll just see how it goes. Now I've also done experiments with 6 coils and 12 coils, but I don't need to show them here. Thank you very much.